So, there are going to be two talks that I'm doing, and the second talk is about more physical things. This is a kind of pure mathematics talk, and it's about Khovanov homology, because I'm going to be using some results from Khovanov homology in the second talk. So I thought it would be fun to give you a little overview about Khovanov homology in this first talk. This is a well-known Escher drawing, rather knotted, I think. And the title of this talk is Elements of Khovanov homology. And maybe you already know about Khovanov homology, but I am kind of rearranging things a bit, so we'll see. Of course, going back to the beginning about the knot problem, the problem is that you can have things in front of you that are maybe knotted or maybe not unknotted, but it's rather difficult to tell. And all of our knot invariants are methods of using mathematical calculation of one kind or another to get an image of the knot in some piece of mathematics in the hopes of understanding it, its complexity. This guy, of course, is unknotted, and maybe you're familiar with him. Can you see that it's unknotted? Well, we can talk about that later if you wish. And then there's the extraordinary complexity of all the knots. This is one version of the knot tables. Knot tables started back in the 19th century with Tate and Guthrie and other people working, Tate and Little, I mean, working very hard to get a tabulation of knots because of Lord Kelvin's theory that atoms, which were beginning to be conceived at that time, were vortices in the luminiferous ether. And so these, from Kelvin's point of view, would be possible patterns of vortices in the luminiferous ether. However, the luminiferous ether disappeared around 1905 when the Michelson-Morley experiment and Einstein's work showed that there wasn't any way to detect it. But of course, it reappears as all of our models of manifolds and spaces. It appears in a different way. And the study of knotting in spaces remains. So it didn't really disappear, but we don't think of atoms as knots, but knots are coming and going throughout physical thinking nevertheless. And here is all this complexity. At least we have to get this to the bottom. Here's another fragment of that knot table. This one from Barnaton's website, and probably drawn through Knotplot. And this is the first sweep of knots up to 8 crossings. This is all of the different minimal diagrams of knots up through 8 crossings. And there's another version of that, courtesy of Junko Takamoto, who, with the help of a local artist, made a Mizuhiki knot table. And so these are like the Mizuhiki knots, decorative knots, but this is a complete table up to 8 sub 21, the table we just saw before, of the knots. And notice that here they are made open-ended, but if you were to close them and compare them with the previous table, you would, I hope, find that they're in perfect correspondence. We haven't checked. I haven't checked. I assume they have. Junko wrote a note to me about that. You don't have to read all of it, but she said Mizuhiki is made from Japanese traditional paper called washi, shaped into a stiff form. Mizuhiki is part of traditional Japanese culture, been around for 1400 years and has been used to decorate gifts for precious people. Additionally, Mizuhiki symbolizes the warding off of evil spirits and the connection between peoples. And I just focused on one of them, that's 818. Probably 818 is actually one that may appear in the actual Mizugiki. I'm sure that some of them don't, but some of them look so symmetrical. You can tell me, someone can tell me whether that one actually occurs, but I don't know. I imagine it would be fun to go back through that chart of Mizugiki knots and figure out exactly which ones actually are found in real practice. Anyway, if we go to another cultural direction, we find Celtic art, where you see a lot of knots. And the interesting thing about those knots is they're almost always alternating. They occur on stones and decorations, and it goes back to around 800 AD. And they're very beautiful, and people wrote many books about these knots. And in particular, David Evans, a statistical physicist around 1990, showed me this book by Romilly Allen, which was written around 1900. And Romilly had a theory for the construction of Celtic knots. His theory being embodied in that little diagram at the bottom of the page on the right. He thought, well, if you make a regular pattern like that, and then you smooth the crossings, as we say, and you see these explained exactly in a mathematician's way, kind of, how to smooth a crossing. You remove the crossing, you put labels on ends, and then you reconnect the ends accordingly, so that either you have vertical smoothing or horizontal smoothing like that, and no crossing anymore. And you can try doing that in different places on the regular knot, and the result will be one of the Celtic knot patterns, of course, other things as well. And if you look over to the right, over to the left for that stone there, you see that you can think about getting those from those. And this, well, you may recognize this because it's something that we use, but we didn't steal it from Romilly Allen, although we could have if we had read Romilly Allen. We finally came to this same idea in a different way for the sake of knot theory. But on the other hand, this idea does permeate Celtic knot work. And for example, you can find a program on the web like this, and it does exactly what Romilly said to do. It will give you a nice big regular pattern like that, and then you can click on those crossings and smooth them one way or another, or return them to the crossing. And as I said, they like alternating, so that the program doesn't have a way to switch the crossing. I thought that was amusing. And so you might go up to the program and switch and smooth some crossings and find yourself with Celtic knot work in front of you. It's interesting, huh? You might try that program if you're interested. So on the mathematical side, circa 1985, we have this bracket idea in the way which I thought about in the wake of the discovery of the Jones polynomial. This ends up being a model for the Jones polynomial, but I didn't know it was at the time when I thought of this idea and then calculated with it and found out, oh, I'm getting the Jones polynomial out of this. But what you have here is an assignment of a polynomial to a knot that satisfies that it's equal to some multiple of smoothing it one way plus some multiple of smoothing it the other way. So this is a mathematician's version of the idea of just simply smoothing it in the two ways, and we're summing over all of the different ways of smoothing it to get this invariant. And it will be an invariant if you choose B correctly and you decide how to evaluate the loop correctly. And then you end up with being able to get something that's invariant under all the Weiermeister moves by normalizing it in this way. Minus A cubed turns out to be what you need to normalize it by taking the power to the sum of the crossing signs of the knot, as you may know already. But in any case, it's a very simple algorithm, but very complicated in the sense that it's very mysterious as to exactly how it's going to behave. You're summing over 2 to the n different combinatorial configurations. And on the other hand, for chirality's sake, it's very interesting because it can tell a lot of chirality. For example, it can tell you that the trephone knot and its mirror image are different. And in general, if you have a knot and you have its mirror image, then the value of the normalized invariant on the mirror image is equal to the value of the invariant on flipping the crossing to it, flipping the variable to its inverse. And so if the polynomial is not invariant under flipping the variable, then the knot had to be chiral, had to be an equivalent to its mirror image. And calculations at the bottom level of this look like this. You simply smooth crossings and add up and get the polynomial. And there are some efficiencies or inefficiencies that are related to the graph theory that underlies all of this. For example, calculating the trephone knot, I smooth it one way and I get a Hopf link, and I smooth it the other way and I get something that I already know how to evaluate. And then looking at the Hopf link, I smooth it the 2 ways and I get things that I already know how to evaluate. And so I only needed 3 out of the 8. I'm actually summing over something that's understandable. I'm summing over trees in some graph. And then that's at least some efficiency. But beyond going to trees in some graph, which gets more and more complicated, the combinatorics is quite wild that underlies this invariant. So we can prove, as this Blackboard demonstration is showing us, that the trephone knot is an equivalent to its mirror image, that the trephone knot is chiral by a few lines like that. But we don't, for example, know when you have a chiral knot, whether this will or will not work. You'd have to compute it. If you believe that some knot is chiral, go ahead, compute the bracket, and maybe the bracket will tell you that it is. But if it doesn't tell you, if it gives you something symmetric, then you better work a little harder and check some other things, because it doesn't mean that it's chiral just because bracket said doesn't know. So that's the first level, and there's lots of sort of straight graph theoretic, look straight at it kind of things that you can do at that level. But then there's another level. Here I have, I'm introducing the other level, but I'm also reminding you what the parameters are. It's when you take the b equal to a inverse and the loop equal to minus a squared minus a to the minus 2, and then it has this behavior under curls that it becomes invariant under second and third Reinemeister moves. But then, as I said, there is this complexity of the states, all of the different combinatorial configurations of smoothings that you have to sum over to get the bracket, and that's very complex. On the other hand, Khovanov looked at this in the late 1990s, and he said, oh, it's a category. Well, it is a category once you look at it that way. That is to say, if you put an arrow between 2 of these states, if one of them has an A that turned into a B in the other one, that's an elementary arrow. Okay, so there's an ordering like that, and you start with all of the states that are labeled entirely A, and you start with the state that's labeled entirely A, and go through all the states until you get to the state that's labeled entirely B. And if you think about that structure, you see that you're looking at a hypercube, in this case, an actual cube. One down, you would be looking at a square. Farther up, you'd be looking at a 4 cube or a 5 cube, depending on how many crossings there are. And you can think of the cubical structure as lying underneath it. You have 3 A's, 2 A's and a B in the next tier, 1 A and 2 B's in the next tier, and 3 B's. And if you think about that, I'll have a picture of a cube in a moment, and you can see how it is related to the structure of a cube. but it is a cube, you can see the cube there. But what can you do with this? You have a category, all right. Now, what did I mean by having a category? I meant, of course, that I'm thinking of the compositionality of these arrows, that I can go from AAA over to AA-B and down into BAB there. I can compose arrows. I can think about the compositionality. I have to add arrows. I have to add an identity arrow to every object. And then I have a category. I have to consider all the compositions of arrows in order to have a category. But then what can I do? Could I measure how the category changes when I do a Reihmeister move? When I do an isotopy on the knot, I'll get a different picture. I'll get a different collection of states. I'll get another category. So how does the category change when you do isotopies on the knot? How do you measure a category? A category is sort of like an abstract space in some sense. In some real sense, it really is very much like a space where it's been put together. But what cells make that space? Could you compute the homology of it in some way? Well, there are ways to compute homology or cohomology of categories, and that exactly is what Khovanov did. He decided on a certain method of computing the homology of this category. And in this case, it's a cubical category. They're all cubes, all hypercubes. And there's a very nice way to describe a homology theory for such a thing. And then it turns out that you can generalize the bracket polynomial to a cohomology theory, which measures this category and ends up, if you choose the algebra right, to be invariant under isotopies of the graph. So that's our task for the rest of today, to this lecture, to kind of show you how this homology theory of Khovanov gets put together and how it happens. And so I'm going to be talking about I'm going to go into it in one way or another, and by the end we will be able to say, well, we've assembled it and it has some nice properties. So that's what we're trying to do here. Now let's see what there. So one thing I'm going to do is I'm going to change my algebra just a little bit. Khovanov did this, and it's actually a good idea for our purposes here. I'm going to, instead of writing the bracket as something times the A smoothing plus B times something times the B smoothing, I'm going to change the coefficients. So the A smoothing gets a 1, and the B smoothing gets a minus Q. And I remind you, let me see, is there a pointer here? One of these. Usually there's a pointer. This guy, thank you. Okay, whoops. Right. So I remind you, if you smooth it this way, I call it an A smoothing. And if you smooth it this way, I call it a B smoothing. And when I say A smoothing, I mean it's the smoothing that was obtained if you join these two regions, and those are the two regions that are swept. If you take the overcrossing line and turn it counterclockwise. Another way of saying what the A regions are is that you're walking along the undercrossing line, and to your left will be the A. Your right is the B. If you're walking along that undercrossing line, to the left is the A. So that's the A smoothing. And this is the B smoothing, but I will continue to refer to that as the A and the B smoothings, but I'm putting a minus Q on the B smoothing and a 1 on the A smoothing. You can think of that as multiplying the whole polynomial by A to the minus C of K, where C is the number of crossings, and then replacing A by minus Q inverse. Or you can just say, I changed my coefficients, and then the value of the loop, it turns out, should now be Q plus Q inverse, which is simpler, and that's one of the reasons for making the change. It's a lot simpler to look at minus Q plus Q inverse than to look at minus A and minus A squared and so on. So if there's a loop, you multiply by Q plus Q inverse. Okay, so we've absorbed that convention. And then I just want to show you what happens with that convention. If you calculate a curl, then you find that it multiplies by Q inverse for a positive curl and minus Q squared weird for a negative curl. And on the other hand, if you look at a Reidemeister 2 move and check what happens, it multiplies by minus Q. And if you do a 3 move, it's invariant. Okay, easy calculations to see, not your favorite multiples, but that means you can normalize it by multiplying by an appropriate thing, and it'll be invariant under all 3 Reidemeister rules. So we're going to use that one, and in fact, this is the normalization. If you defined it this way, the way I just did, then if you take -1 to the number of negative crossings, it's an oriented knot, just like the one where you calculate the rise, right? And you take -1 to the number of negative crossings, and then Q to the number of positive crossings -2 times the number of negative crossings. Remember, it behaved differently under a positive and a negative curl. One was Q squared, the other was 1. So that normalizes it, and then it's invariant under all 3 of the moves. So we could call this the Jones polynomial, although you probably have to change Q to T root T or something. And then you get the Jones polynomial out of that. So we'll call JK of Q Jones polynomial that way. And that's what I'm going to be using. I'm rewriting it and thinking about how the states get weighted by powers of Q. That's one change. Next change. And this is a very nice idea due to Oleg Bureau. He said, let's get rid of the powers of Q plus Q inverse that are going to appear, because you have loops, right? And every loop gets evaluated as Q plus Q inverse. And so if you had 20 loops, you'd have Q plus Q inverse to the 20th, and you'd apply the binomial theorem and get a whole bunch of terms when you're working out the bracket. But we're going to get rid of the binomial theorem and have more complicated states. So now the states will have labels on their loops, +1, -1, like that. And then the value of this loop is equal to the sum of Q and Q inverse. All right, fine. What will happen if I had 2 loops? Well, if I have 1 loop, I have Q plus Q inverse. If I have 2, I have, as you see, I have plus plus, plus minus, minus plus, and minus minus. I have 8 states. And this is Q squared, and that's Q times Q inverse, and that's Q inverse times Q, and that's Q to the -2. And if you add those up, you see that you're exactly getting Q plus Q inverse squared. And of course, it will work in general. You have 3 loops or any number of loops, and you consider all ways of labeling them with pluses and minuses, and add up the evaluations of them, you get Q plus Q inverse to that power. So therefore we can, instead of having the binomial theorem in the expansion of the polynomial, we have all these extra pluses or minuses on the loops. And then I'm telling you a convention. Perhaps I should have waited. But it turns out that it's a good idea to call the labeling by -1 X and the labeling by +1 1, and you'll see why in a few minutes. But I'm going to do that. I'm going to have a label change called X and 1 rather than -1 and 1. But now we have a formula for the bracket in terms of these enhanced states. And see if you believe me. Think about the bracket. You're going to have -1 to the number of B smoothings, because the only place where a -1 occurred was when I did a B smoothing. There were no funny -1s in the evaluation of a loop. There are -1s. They give us a lot of trouble, right? Because we'd like to know, when does this polynomial collapse? It has -1s in it, so sometimes things can collapse, and some, perhaps for some not, the polynomial is 1. We don't know. We've never seen a knotted knot with polynomial 1. So that's the -1 to the number of B smoothings in this state. And then there's a power of Q. And only the power of Q, right? But what contributes to the power of Q? Well, the number of B smoothings, because every time you get a B smoothing, you get a Q. But also, you get a Q to the +1 every time you have a loop labeled +1. And you get a Q to the -1 every time you get a loop labeled -1. So therefore, you get that the power of Q is the number of B smoothings plus lambda, where lambda is equal to the number of +1 loops minus the number of -1 loops. So I'm going to call that J, and then I have a nice theoretical formula for the bracket in the Q form as the sum of monomials, sum of nice monomials. And now if you wanted to know what is the coefficient of the power of Q itself, well, you could say, okay, I'll rewrite as the sum over J. Just think of doing this in your head. You rewrite as the sum over J, and then you have to take in here the sum of all these different signs that can occur depending on that value of J, where J is equal to this. You rewrite it. So I could rewrite it this way. I could say it's just -1 to the I, Q to the J, my I, J. And then I'm going to count how many states are there with that I and that J. In other words, I ask how many states are there that have this many B smoothings and have a J of that form. So, you know, without a knot in front of you, you can't do that count. But with a knot in front of you, you could say I choose I equal to 1 and J equal to 3. And how many states are there that have I equal 1, 3, 1 B smoothing, and have the J value equal to 3? I go through the list, I find them. Then dimension, I'm just doing this with analysis of forethought. The dimension is just the count of the number of states that have I and J fixed. Okay. Now I'm calling it a dimension because I'm thinking forward into how this is going to work. And we're going to take a module whose basis is those states that have a specific I and a specific J. Okay, so I'm going to go from counting states to making a module. And I'm looking at all the states together and they form a big module. For every enhanced state, I can talk about 3 times it, or I can add a couple of states formally, and I get a big module. And that module is going to turn into the chain complex in the end. So this is the restricted part of the complex. It's just, whoops. It's just exactly those states that have a specific value for I and a specific value for J. All right. And at this point, it's beginning to look like maybe that ought to be something like homology. You can see ahead now, because you could sum this on J, and then you would have the sum on I of -1 to the I dimension of Cij. And if you're used to a little homology, then that looks to you like the Euler characteristic of something. So it's beginning to appear. The pattern on after is beginning to appear. So what I want then is a differential, because we're looking to create homology. And the differential should, I hope, take Cij into Ci plus 1j. And that's the way we're going to set this up. You'll see it happens naturally. The J won't change and the I changes, so that each one of these for a fixed J becomes a complex whose homology you could measure. And then you can ask yourself, what would do that? What would keep the J fixed, even though the I increased? And for that, you want to go back to this bit that you have by now memorized. Maybe, in fact, if you're following this for the first time and you're not used to this notation, you might jot this down, right? -1 to the number of B's, Q to the J, and J is the number of B's plus lambda, where lambda is equal to the number of +1s minus the number of -1s. If I want J to remain the same, and this went up by 1, then this would have to go down by. That's all I'm saying. We'll come to it in its concrete life in a moment. Now, the boundary that I'm thinking of should go in the same direction as our smoothing arrows in the category. So these are the ideas behind the boundary. It's going this way, but this is only one fragment of boundary that I'm computing. It's one smoothing turning into the other smoothing, but I think of that as the generating boundary map. There has to be a map from the module that's associated to this to the module that's associated to that. And furthermore, it's very useful to think of that mapping as corresponding to a surface whose boundary is one state at the top and the other state at the bottom, and goes through a saddle point as you go from one to the other. That's an associated idea, but of course, since we're thinking in category terms, you can immediately imagine another category in which a surface going from one thing to another is a map in the category. Any darn thing that can be given a directionality and has some compositionality can be thought of as generating some category or maps, right? As long as you can put things together, then you have the possibility of a category. And if you have a surface that goes from here to here, and you have another surface that goes from here to here, then you have a surface that goes from here to here. So you have some compositionality, and that compositionality here turns out to be very important. And in fact, you might suspect that one intuition behind what we're trying to do is to understand how a surface, how knots are behaving when you change surfaces that bound them. And certainly we're asking some question about that, but here we're using it to make the construct. So here we are back at our nice formula for the bracket. And this formula is recollected, as I said, into a sum on j, q to the j, and then sum on I minus 1 to the I dimension of Cij. J is fixed. And this would be the Euler characteristic by definition. That's the definition of the Euler characteristic of a complex with parts Ci, j fixed, of this complex, which depends on j. So we have that this is true if there were a complex, or we could just, if we had a sequence of modules, we could define this to be the Euler characteristic of a module. I remind you again, Euler characteristic is coming from Euler, who first discovered that if you take the graph in the plane and you take the number of vertices minus the number of edges plus the number of faces, it's a topological invariant of the plane. Doesn't depend on anything but the connectivity of the graph, and equals 2 in the plane. And if you were on a surface, you would get 2 minus 2g. You're getting the genus of the surface, and the Euler characteristic there for Euler is equal to the number of 0-dimensional things minus the number of 1-dimensional things plus the number of 2-dimensional things. So when the topologists got hold of that and started thinking about higher dimensional spaces, they defined the Euler characteristic to be equal to the number of 0-dimensional things minus the number of 1-dimensional things plus the number of 2-dimensional things minus the number of 3-dimensional things plus the number of 4-dimensional things, and so on out to the end of the space. And so that's algebraically what we're talking about here, minus 1 to the I dimension of the I-dimensional things, where that I has now become kind of abstract. What dimension are we talking about here? But that's it. And so we now have a beautiful formula for the bracket as its coefficient of the q to the j is the Euler characteristic of this complex. And then if we give it a differential, then it is a homological algebra fact that the Euler characteristic of the homology of it is equal to the Euler characteristic of the complex. So that's how Euler got generalized. The sum of dimensional bits alternatingly is equal to some topological number about the space. That was that is the generalization of what Euler found. And then we would have that the bracket is equal to the sum of Q to the J, or the characteristic of some homology. Now that homology is going to be the Khovanov homology, and it's going to be invariant, and invariant is not. And it's more general than the bracket, but the bracket can be retrieved from it by taking a graded Euler characteristic, where the grading word is coming in, because there are a lot of different homologies for each, one for each J, and you add them all up. It looks a little complicated, but on the other hand, you see that this much, the fact that the bracket coefficients look like Euler characteristics, is coming just from thinking about the combinatorial structure of it. That shadow of it is there. Now it's going to turn out that the this slide is in the wrong place. I might use it, but I'll come back to it. But this one is not really in the wrong place. What I called C1 was when there's one B, and what I called C2 was when there's two B's, and what I called C3 is when there's three B's. This is the I, not the J. The J is hidden because we haven't labeled these states with pluses or minuses. So that's the first gradient, that's the homological gradient. And if we do get a complex, this looks a little strange. It's going to, our boundary map is going to raise the index. But that's the way it's going to work. So if you're trying to think of it as a boundary map, then this is the highest dimensional part and this is the lowest dimensional part. But we haven't actually filled in any space for you. So you can think of it any way you like, but the grading goes up when you take the boundary. And what is the boundary map going to be? Well, it's going to be some sum of maps corresponding to each one of these arrows. Each arrow is going to be a map of modules. And we're going to take a sum of these maps, and that will be this one. And we're going to take a sum of all these maps, and that will be this one. And the module here is going to be the sum of all of these. Because you're supposed to be allowed to add somebody in here with somebody in here to form the big module that we already described. We said that we would just form a module out of all of the enhanced states. So that means that if I wish to, I could take somebody in here and add it to somebody in here freely. And then the C1 is the direct sum of these, or the sum of these, and so on down the line. So that's the form in which we're going to use it. The rule for the signs is very simple and looks like rules that happen in algebraic topology. That is, every one of these maps has to have a sign assigned to it. I'm going to tell you how to map from one of these to the other simply without putting any sign. But then I'm going to tell you something like, take this one plus, take this one minus, take this one plus. And I'm going to do it in such a way that when you do two of these in a row, you get zero, because that is what we're looking for if we're going to make a chain complex. We want the boundary of the boundary to be equal to zero. And in order to do that, you need to put in some orientation signs. You remember it from calculating ordinary homology, if you ever did. But the rule here is simple enough. If you go from AAA to BAA, you will do that map with a plus sign. But if you go here, eliminating this B, you're going to take it with a minus. And if you go all the way over here, you take it with a plus. You just alternate. If it's all A's, you just alternate. No plus, minus, plus, like that. And if there was another one, minus, and then another one, plus, if it's all A's. If it's B's and A's, and you're taking a boundary, then you ignore the B's and just look at the A's. So it'd be plus at this elimination, minus at this one, and so on. And that's the rule. Very simple rule. Okay. And as I said, this is what I'm after. I'm after a boundary map that keeps the number of J fixed and raises I. And let's see if we can find it. So I have a plus and a plus. And I'm going to smooth it. Now we're doing a really concrete exercise. So you don't have to remember the things I asked you to remember. I'm going to smooth this crossing. I'm just going to re-smooth this, sorry. And lambda is 2 here because I have 2 pluses. And I want to have lambda go down by 1. Lambda should be 1. And I have to put a sign on this loop from 2 to 1. Well, a plus sign is what I have to do. I have no choice. So that's what happens here. Now, if I have a plus sign and a minus sign, lambda is 0, and I have to go to lambda equals -1. And now the only thing I can do is label it with -1. And if I have 2 minus signs, lambda is -2, and I can't get to lambda equals -3 on a single loop. So I call it 0. And that's how to do this. Now, how can I describe what I did so I can remember it? Well, remember I said that minus should be thought of as x and plus should be thought of as 1. And then this says 1 times 1 is 1. This says 1 times x is x. This says x times x is 0. So far, for the part where you take 2 loops to 1 loop, which is the product in something, I'm going to be having x squared equal to 0. And I am looking at the ring Z of x, polynomials in x, modulo x squared equals 0. That gives me a product on the module V, that ring, which is given by 1 behaves like 1, x is behaving so that its square is equal to 0. And we have the module generated by that. And that module corresponds to 1 circle. The generators for 1 circle are plus and minus. Those are 1 and x. So the first simplest module that I have to work with is taking a circle and thinking of it as a module generated by 1 and x, which corresponds to the labelings that I'm using, plus and minus. And the x squared equals 0 makes that multiplication work for what I'm trying to do to create a boundary map. Now I also need to think about coproducts because 2 circles might smooth, 1 circle might smooth into 2 circles. Let's look at what happens there. I start with labeled x, it's lambda's -1. I split into 2 circles and I want -2. And the only way I can get -2 is have both these minus. Okay, so delta of x is x tensor x. And tensor is a formal way of talking about 2 circles, right? Product of 2 circles. When we have 2 circles, we are going to take the tensor product of the module for 1 with the module for the other. Okay. Now, what happens with labeled 1? Well, I'm supposed to get to 0, and I can get to 0 with +1 and -1, or -1 and +1. So I better be an equal opportunity employer of this business and give it both with equal weighting. That's a good choice. So I take that delta of 1 is 1 tensor x plus x tensor 1. And now I have translated the coproduct part of the boundary mapping into algebra. And I have 2 formulas. Delta of x is x tensor x, and delta of 1 is 1 tensor x plus x tensor 1. So I now have a structure on this simple module, which already has a multiplication. I have a co-multiplication defined on it. And that together forms what is called the Frobenius algebra, but let me not go defining a Frobenius algebra. Let's just call this our Frobenius algebra, and we will see what properties these algebras are supposed to have in a little bit, and then I could say something about what a Frobenius algebra is. But what happens here is that you get a nice little well-defined algebra with a product and a coproduct, and that gadget is telling you how to take the boundary. Okay, so this requires layers of things to build, and this little algebra is nice to carry around in your pocket because it turns out that it really does work. Once we define homology by using these boundary maps and the method of signs that I just showed you, it turns out to be invariant under the Reidemeister rules. Who would have thought it, right? not obvious. Although I have to tell you that I asked Khovanov years ago, I said to him, well, did you know when you invented this, and how soon did you know that it was going to be invariant? And he said he knew it was going to be invariant. So how soon does one know that this is invariant? I don't think you know at this stage that what I've done is going to be invariant. Or if you see a way to see from here that it's surely going to give us an invariant of knots, I'd like to know what story you tell. Okay. Now, one thing we want to find out about this, and I'm just giving you one example, is that it should not depend on the order in which you did it. That is, what I'm doing here is first, let's see, who's first? The first I'm going to do this smoothing, I'm going to do a multiplication, and then I'm going to do the co-multiplication that corresponds to smoothing that one. So you see, you've got two crossings, and I'm thinking of iterating the boundary, right? So first I did the boundary map and did this one, and then I've got this one and I'm doing a boundary map and I did this one. In the category, it means that I went whoop, here, and I went here, and I went 2 steps. And I'm looking at what happens in 2 steps. And what I want is that if I do this, that, it should be the same as if I did this and that. I want it to commute. I would like it to commute. If I can make it commute, then that means that mod 2 boundary is 0, because every time you did it this way, you'd also have a term where you did it this way and you get 2 multiplying every term that you got when you did it twice. And so mod 2 it'll be 0, and then those signs will make it work over the integers. That's what happens in ordinary chain complexes, and it's not going to happen here. So I want to see that it didn't matter in what order I did it. Well, let's do the computation. I do multiplication first. I start with them labeled 1. 1 times 1 is 1. Then I do co-multiplication, and I get 1 tensor x plus x tensor 1. Now here. Now I did it in the other order. The other order meant I co-multiplied here. Okay, I get 1 tensor x plus x tensor 1. And 1 got carried along, so I got tensoring with 1 here. Now, then my next act is to multiply here, which means in the second 2. Sorry, that's a little unreadable, but I'm multiplying x times 1 and 1 times 1. And so I just get 1 tensor x and x tensor 1 again. It works. And I'm only doing one example of this, but you can do a whole bunch of examples that go through all the different cases. They all work. Okay, so this algebra has the nice property of giving you compatible answers independent of the order in which you did that. And another thing to notice is that we went to this geometric idea of compositionality, where we're composing these little cobordisms. And this cobordism this surface cobordism here is homeomorphic to this surface cobordism here. Push that saddle down, push this saddle up, right? So, in fact, it turns out that that's what this algebra is doing. It is actually producing mappings, surface cobordisms, and the mappings that you get are always the same whenever the surface cobordisms are homeomorphic. So there's some topology going on in the boundary mapping for this complex. Okay, that's the way it works. And we can think about the structures of these mappings. What is very useful is to think about the surface cobordisms a little farther and add a couple of extra things. Well, because for example, you might want to think of a surface cobordism like this. In the world of all surface cobordisms, you could have one like this, where you went down and you went through a co-multiplication, and then you went through a death. The circle died out, and then you went over to this circle, and you would like to have a mapping that corresponded to that, to complete your picture of having mappings corresponding to surfaces. And that means you should have a mapping that goes from a circle to the Z. Or the module. You should have a mapping that goes to the module. And you should also have a mapping that goes from the module over to the module of the circle. So you want to go from module to scalars and from scalars to module. Like that. That's called a co-unit, and this is called a unit. And then I could write down what that is doing with the algebra if I wanted to. But I'm going to maybe we ought to follow it out just so we're careful here. I got this far and I got delta of A, and delta of A would be some sum of tensor products, one here and one there, right? Then I'm going to apply epsilon on the left tensor product, one on the right. So I have the sum of epsilon of A1 tensor A2. And then I'm multiplying them to get to here. So I take the multiplication of these, so that's the sum of this times that. And then I would like this to be equal to just A. This should just be the identity, nothing happened, right? So that's a formula that defines the basic property of the co-unit. That a unit multiplies by one and leaves something alone, but a co-unit sums over the co-product, the epsilon on the left piece, and ends up being equal to the reassembling the original thing. That's what a co-product does. So if you took A equal to 1, then you would get 1 tensor x and x tensor 1, and then you would get multiply epsilon of 1 times x plus epsilon of x times 1 should be equal to 1, which says epsilon of 1 times x plus epsilon of x times 1 equals 1. Oh my gosh. Well, we could have that happen if epsilon of 1 was 0 and epsilon of x was equal to 1. And now we found out what epsilon should do. Epsilon should be 0 on 1 and 1 on x, and now we know how to extend our algebra to have an epsilon. By the time we have an epsilon, we really do have a Frobenius algebra. And then we can find out evaluations of other mappings, like what happens if I go from scalars through a sphere and back to scalars. Well, take a look. You've got a 1 here. Then you've got a 1 here because the co-unit of 1 is going to be 1. That's the definition of, the unit on 1 just pushes the unit forward. But now we get 1 tensor x plus x tensor 1 because we went through co-product there. And now we're going to be multiplying and we get 2x. And then we're epsiloning, and epsilon of x is 1 and we get 2. So that tells us that the value of a little sphere is 2. So now we have evaluations for various surfaces. You'll find that if you had a torus, if you have a, gosh, I'm speaking incoherently here, I'm sorry. Go slowly. The value of a sphere is 0. The value of the sphere is 0 because of the same kind of calculation, but the value of the torus, which is what we just went through, is 2. And we find that any surface I write down, it'll have an evaluation. Toruses are true, spheres are 0, and we can go on thinking about that. So there's all this little the extra topology going on with the surfaces there and our boundary. It's worth paying attention to that. So there we are. Now, let's talk about the cubes a little bit more. And you'll see we're going to wander into assembling this a little further. The structure of a cube, if you were to divide its sides into an A and a B, is exactly the same as the structure of our cube category, right? So you begin to realize that this cube category is like a retrograde step. In the old days, it used to be that people would think of A plus B squared, and in order to understand it, they would think about this picture. By now, people don't even teach this picture necessarily, but that picture is actually the categorical form of some kind of form of A plus B squared. And a nice exercise in thinking about categories is to do that, to think of generalizing A plus B squared to A arrow B squared or A arrow B cubed. I'll explain what I mean in a moment, but just look at the cube category here for, for a real cube. And realize that our cube category is actually in one-to-one correspondence with the decomposition of a cube into sides A and B, A plus B cubed, where you have A cubed here and you have a B cubed down there, and two things that share a face have a morphism between them. So that you're actually putting, by thinking in terms of these categories, you're actually thinking concretely about the geometric structures that you had forgotten since the 1500s, when it became much easier to solve cubics, not by using these things as the background out of which you're doing your algebra, but just doing ordinary algebra. But here we're reconstructing some of the geometry when we do these categories. I guess that's all I wanted to say about that. I could reconstruct the algebra by giving rules for multiplying Arab things together and collapsing them, but I don't think I did that in this slideshow. Okay, but now I want to keep thinking about this as geometrically as I can. So I'm thinking about surface cobordisms whenever I have one of these mappings. And I'm repeating what I did before. I can think about surface cobordisms corresponding to the mappings involved. And strictly speaking, I'm going back and forth in my mind between the abstraction of the cube category and the realization of it as another combinatorial category, namely the states and all their arrows. We can think that way. But then these mappings are surface mappings, that surface cobordisms that go from here to here. There's a little surface that connects this to this. There's another surface that connects this to this. There's a composite of two surfaces that connects this to this. And these mappings commute in the sense that the surface that I get by doing this is homeomorphic to the surface that I get by doing this. And we use that in constructing the algebra that I just told you about. But now I'm forgetting the algebra and just thinking more carefully about the surfaces and how they're related to one another. Okay? So then we get a big idea, which is very nice due to our requirement time. The paper is Tangles and Khovanov Homology's second paper he wrote on that. You'll find it in the internet. So I've just stated the principle. We're going to use an abstract categorical analog of the chain complex. And it can be taken up to chain homotopy, where chain homotopy is going to be described abstractly, and we're adding the maps, we're adding the maps formally. That is to say, let me go back to a picture of one of these. Here's our category again. And I want to think about this category without the algebra. I just want to think of it as a category, but I have added topology to it in exactly the way we've been talking. Every mapping you look at is a surface that goes between these two. Different surfaces for different arrows. But if you go from here to here and then over to here, you have a surface that goes all the way along from here to here. And these commute because the surfaces are homeomorphic. And I'm going to think of formally a chain complex, but it's not going to have algebra in it yet, by allowing myself to add mappings. Like if I have this mapping to here and this mapping to here, then the sum of these two mappings would go to the sum of these two, which is just formal sum of these. And then our chain complex reappears as this goes to the sum of these, to the sum of these, and to the sum of these. But I'm only thinking about the cobordisms. I'm just thinking about the geometry of those mappings. Where is this going? Well, let's see. I want to remind you what a chain homotopy is about. I say that two maps are chain homotopic if there exists an H from the complex that on which one of them rests to the other complex, so that the boundary of H plus H composed with boundary is equal to the difference between the two maps. Have you ever seen that before? We need to recall. You have two maps. I'm thinking geometrically. I have two maps from a space to another space, F and G. And I'm looking at a homotopy, which means that I have a mapping from X across the unit interval, F, into Y. And at one end, you get F, and at the other end of F, you get G. And if you looked at the image of an X, some X, under the homotopy, then the homotopy would be showing you the G F of X at one end and the G of X at the other end, and in between all these other images that are happening because you have X cross I. So if you sliced it this way, this would be F of X cross 1/2. Up at this end, you have F of X. At this end, you have G of X. And the boundary of this object here, which is one dimension higher in spaces, is equal to F of X minus G of X, and then H on the boundary of X. That's these lines on the other side. So you have a formula, a formal formula. The boundary of the homotopy applied to X is equal to F of X plus G of X plus H applied to the boundary of X, which we can then rewrite as boundary H minus H boundary equals X plus G of X, or with some minus signs. I'll work mod 2 from here on. So that's a chain, that's a homotopy at the level of homotopies described geometrically, but the image in chain complexes is the same. Here's a chain complex, here's another chain complex, here's a mapping between them. We say the two chain complexes are homotopic to one another. The two maps are homotopic to one another if there is an H, which takes us from this one up to this one by shifting up one dimension, because this is higher dimensional, and satisfies boundary H minus H boundary equals F plus G, or the other way around. I should have all said this all not true. Okay, so that's what I mean by a chain homotopy, and I can define a chain homotopy without having any algebra underneath. It came from a place where I defined it without any algebra underneath. I'm thinking about homotopy of spaces, and you have that kind of decomposition. You'll notice my signs got switched around, so you should read everything mod 2 from here on out, and then everything will be fine. But we want that the boundary of H and the H applied to the boundary fill out to the difference between F and G on the top and the bottom. So then I have a notion of two of these generalized, these categories with their cobordisms going on, and I have another category with its cobordisms going on, and I can think of mappings between them, and I will say that two of them are chain homotopically equivalent if there's maps between them that form a chain homotopy equivalence between them, which means that the compositions of F and G on this side is chain homotopic to the identity, and the composition in the other side is chain homotopic to the identity. Then if you were doing homology, you get the same homology. But here we're not yet doing homology. We're just up here in this compositional situation with these surfaces, and we're saying that we'll call them homotopically equivalent. And then Dror's notion is, okay, so we take the chain homotopy class of that category. So we have the Khovanov category. There's no algebra here yet. We just have the Khovanov category with all these surfaces going everywhere. And we take its chain homotopy equivalence class. It's a kind of homotopy theory for these categories. And that's the Khovanov homology in the abstract. And we're going to ask, what do we need for that to be invariant under Reidemeister rules? And that's why I'm worrying about it. Because if I go up to that level, then it's possible to think simply and understand what you need in order to get the thing to be invariant under the Reidemeister rules. And I'll do that. And then we can come back into the algebra and find out that the algebra that we have discovered indeed is good for that. Okay, so we can get an appropriate insight about why it's working by doing this. So here we are. You'll see in a moment. Here I am. I've got a Reidemeister 2 move, which is the only one I'm going to analyze. I got a Reidemeister 2 move here. I undid it. If I undid it, then locally my category looks just like this. Of course, there's a lot of other stuff, but that's all behind the screen because you only see this bit of diagram. So this is the category. This is how my category looks before the Reidemeister rule. But after the Reidemeister rule, I have a bunch of smoothings and resmoothings. So I have this little square, right? And now I'm comparing this category with this category. And now you see something that I could have worried about before. If it had only been categories that I was comparing, I would be worried at this point because I would like to compare this with this, and that's fine. It compares perfectly. But I also would like to compare it with this. And how am I supposed to compare one object with two objects in the other category? In trying to compare one category with the other, I end up with a single object in one of the categories wants to be compared with two objects in the other. I need a different category over there on the other side. But we already told you what to do. We said we were going to add these. And of course, that's what we did originally, and we're going to add these. We're going to have the direct sum of these. And then the new object is the direct sum of these. And I can take a map, I can define a map from an object to a direct sum of objects. I can actually map into both of them. I could say x goes to x squared in one and x to the seventh in the other, and add them up. So I'm allowed to do that because, in fact, I am taking the direct sum in this direction, a long constant number of b's. So that's okay. That's okay. Now, comparing this to the upper line, there's no problem. You just map it identically. But I also am going to map it to the lower line, and what is my mapping? I have the mappings, they're there, geometrical. In this mapping, I give birth to a circle. So that was product or co-product, right? Circle can go from nothing, and I put this in. So there's a little surface cobordism from nothing up to a circle. Good. And in this direction, I take this circle and I let it die, and it goes here. So I have G1 is circle dies, F1 circle is given birth to, and I have these two mappings. Now, what about this way? Boundary 2 going over here is smoothing this crossing here. And that's going through a little saddle. You'll have a picture of it. Boundary 1 is smoothing this crossing, and that gives birth to a circle by smoothing. H1, the only mapping you can think of is to let that circle die. And H2 is to give birth to a circle. And those are the ones that go against the direction of the chain complex. They're going down dimensionally in the way I indexed it, but you should think of chain homotopy mappings as going in the opposite direction from the way the chain complex runs, right? That's what I mean. So those two there are my candidate chain homotopy maps. They're the only ones I can think of, so I put them in. And now we have the bottom line. There's the bottom line, the one we were just discussing. And here are pictures of the various maps. F1 goes from these to giving birth to a circle. G1 lets a circle die. Boundary 1, you see how boundary 1 gives birth to a circle, but not strictly birth. It goes through a saddle. Boundary 2 lets a circle die by going through a saddle point. H1 lets a circle die, and H2 gives birth to a circle. And we have these maps, and I want to now assemble them in the form of writing down the chain homotopy that I want. And here's the chain homotopy that I want. I want that if I go from here down to G1 and back to F1, that should be equivalent to the identity along this part. That's the piece of chain homotopy that I want. Now I'm working mod 2, so I wrote plus the identity. And then I have H1 boundary 1 plus boundary 2 H2. H1 was the one that let a circle go away, and then boundary 1 revert the circle through the boundary. And boundary 2 let a circle go away and revert the circle through a boundary. And we have all 4 of them assembled here. And now there is a pattern that you can see. Maybe it's better shown in the next slide. Yep. So I eliminated all the labels, and this is the same as what I did before, but now you're just looking at it as a picture of 4 surface things. And what you see is 4 bits of surface. Number 1 is this wall here. Number 2 is this wall here. Then you have this little bowl here and another bowl here. 4 bits of surface. And then in the first one, 1 and 2 have been connected by a tube. In the second one, 3 and 4 have been connected by a tube. In this one, 1 and 4, and in this one, 3 and 2. So you have 4 surfaces and 4 turns, and in each turn you connect 2 of the surfaces by a tube. And you can assemble the whole thing, so you're thinking 1 and 2, 3 and 4, 1 and 4, and 2 and 3. There's some patterning there. I won't bother you with it. I'll rewrite it, but I can rewrite it this way. 1, 2, minus 2, 3, plus 3, 4, minus 1, 4. That turns out to be what happens when you wake up, get rid of mod 2 and go back into the signs. It's a full relation like that. And that relation among tubing of surfaces in the cobordisms is what you need in order for it to be invariant, in order to get topology to come out of it. So this is the story without any algebra. Now, I don't know how to motivate the story without telling you about the algebra. So I told you about the algebra first, and then I let go of the algebra, and we have the story. But think about the story for a moment. It's actually very simple. You have the Khovanov complex, you have the state, the set of states, and between any 2 states, there's a surface because you went through a saddle to do the smoothing. And there you have the compositionality of that. And you have this structure. And what we've shown is that if we think of this structure as an abstract chain complex by adding up appropriate things along the B's so that so single objects could be compared with multiple objects, you got that gadget. And then you take it up to chain homotopy. The chain homotopies appear naturally right there in front of you. And you get this relation that you need, which is this 4-tube relation that I just drew on the board. And if you then mod out all the cobordisms by the 4-tube relation, you're going to get a topological invariant of knots and links. So we analyzed it from the point of view of topological invariance of knots and links. And then you can go back and find out that now I'm repeating this in some different form. So it's sometimes useful to just, instead of writing a surface, to just write a little line and a wiggle meaning a tube, right? That's useful. And then I would write the 4-tube relation this way. And then this is important. If you then think of, it's any 4 regions that can be tubed. So I can have a surface here and a surface here, and 2 regions in one and 2 regions in the other. And then we have 1 and 4 and 2 and 3 tubed, or 1 and 2 and 4 and 3 tubed. And if we rewrite that in terms of surfaces, you see we get 2 tubes here. This is 2 copies of a tube from here, and a tube from this to itself, and a tube from that to itself. A tube from something to itself is a little torus thing. And so I get that 2 should be equal to 1/2 dividing by 2 if I could. Little torus on top, little torus on the bottom. And little torus in our algebra corresponds to multiplying by x, and you end up, that I'm going to leave for you to think about because we're out of time. But we get a tube relation, and that tube relation can then be understood to be equivalent, algebraically equivalent to our 4-tube relation. Once you play around with it, you can go from here back to here. And this one is more algebraic. This one says that any x is going to be equal to some formula involving epsilon of x times something and so on. Any a. I'll show you what it looks like in a slide. We'll skip that. It looks like this. It looks like alpha going straight down through the tube should be equal to epsilon of alpha times x, that's the dot, plus epsilon of alpha times x, that's the other dot. And you get an algebraic relation that corresponds to the 4-tube relation. And tracing that back in, you find out, that actually is true in the algebra that we had. But furthermore, if you look carefully, you find out that there is, I'm going to skip to here, there is a generalization of the algebra that we had that still satisfies the 4-tube relation. And so you get Khovanov homology on a range of algebras, and the 2 extreme algebras that are involved are k equals 0, the one we were looking at to begin with, and k equals 1, which is called Lee's algebra. Yun Su Lee, who wrote a paper about that before this connection was understood. And Lee's algebra is a simpler kind of homology theory. And then it turns out that by combining Lee's algebra and Khovanov's algebra, one can get very subtle invariance of knots and links through the work of Rasmussen. And that's called the Rasmussen invariant. And we have enough time to, we're at -2 minutes. So I should just go to the end. Lee's algebra can be analyzed a little bit. Lee's algebra has it's very easy to think of different kinds of things that you can do to calculate Lee's algebra. Lee's algebra is simple, it turns out. And in the end, you get an invariant due to Rasmussen, which looks at the relationship between the 2 algebras and calculates a certain thing from the relationship between the 2 algebras. And it has some nice property, which I wanted to state to finish. It has these nice properties. It's additive under connected sum. If you have a mirror image, it changes sign. If you have a positive knot diagram, then it's equal to the number of crossings minus the number of Seifert circles, the number of smoothing circles, if you smooth everybody in an oriented way, plus 1. That's twice the genus of a spanning surface for the knot. And that's the key thing that I need for the next lecture, that you get this out of that. And you get that the Rasmussen invariant is a lower bound on the 4-ball genus of the knot. If you have a knot and you try to bound it with a surface in 4 space, the Rasmussen invariant says the genus can't be less than a certain amount. And if you have a positive knot, then you can calculate it, positive crossings, then you can calculate the genus very easily, but often because of the fact that you have this inequality. And in the case of torus knots, things are very nice and easy, and you find out that the genus of a torus knot is given by A-1 times B-1 over 2, which was conjectured by Milner long ago. Rasmussen tells you that. And so that's the kind of very beautiful information that eventually one can assemble out of this foray into a whole collection of ideas that take a long time really to get used to, I think. But the invariant is very valuable, and that's my sketch of Khovanov homology And I'll stop.